Hope everybody is back. So we're going to try to do all of that now remotely. You saw it was already decently aligned, got sub-angstrom resolution. If I open the beam, we see it is in focus. But what I want to do is, I want to make it a little bit more challenging. And I go back to where I started this morning during my breakfast. Having remote control is a nice thing. I mean, by the time you come to the lab, it's already aligned. Okay, so I go back. Oh no, it's the wrong thing. Okay, that was dumb. It happens. So I pressed the wrong button. So we now have a good aligned microscope. So let's see how well we can go on from there. It's not the full experience. So I go here. I wanted to show at least a few things on the röntgengram. Let's see whether I can have my... You see how awkward it is to operate that microscope? Okay, here's a right-hand panel. Can I somehow... Yeah, it's somehow in my way all the time. Good. I'll have to... Okay, now I completely screwed it up. Okay. Maybe I stop sharing and then I share again. Okay, here we are. So if we defocus things, let's... In a röntgengram, you can actually see your sample. So it means I switched. It's on, right? Okay. I switched to a mode where I'm now in between the reciprocal plane, as a backfocal plane, and the image plane. And so I see a diffraction pattern and an image together. It's called a shadow image. And so you can actually position your sample here. You can see what's going on. And then if we zoom in, you can see we actually get to higher and higher magnification. And if you're at infinite magnification, you can go through it as well. Need a smaller. For the one who are seeing it here, it's me. Oh, the defocus step is high. Oh, wow. Okay. I think I nicely screwed up. I nicely screwed up my aberrations. So we go close to this. You can already see a high resolution image when you're at higher magnification, right? And then we are so what we see, it's relatively awkward. So if you have some amount of automatization doing that, that really helps. In the moment, we have 2 grad students, Utkarsh and Kamya, that are having an internship in in California, and for unknown reasons, they want to work on their PhD while there, and so they go on it on Saturdays from California and operate the microscopes that way. And it wouldn't work very well if you're not having some amount of automatization. So now we have it focused. And what we are going to do is I try to at least show you a little bit of how we are doing things. Okay, that's what the problem is. I want to go to a different notebook. To start, ideally, I could have done it differently. So that is the other one. You cannot, for safety reasons, you cannot connect to our microscope. So you have to be LISA, have the right credentials for that, and so on. So if we restart that, I want to make it clear that we are not, hopefully, we recently redesigned everything. And so, so as before, we first load all the different parts, bits and pieces, all the different packages that we need. Here we have now PyTemlib, so that is part of microscopy. All the different microscopy analysis parts are in PyTemlib. In microscopy, there are atom finding, which we do in the hackathon today, and all of that stuff. What we have extra, okay, so there are a few generic parts, packages that come with Python. We have a plotting library, we have a numeric library, and we have some interactive buttons and stuff. But the important part is we have Tango. PyTango is a server software that is running on our microscope, for our microscope. And we have this tiled server that is our data server. After lunch, we'll go a little bit more into that. It's running right now. Actually, it's running all the time. And so what we do is we connect to it and just check whether everything's available. And you can see we have a lot of different stuff available. We can move this stage, scan, EDS, camera. We have our data server on. The instruments is the microscope itself, and then we have the corrector. The corrector is what we want to use together with the microscope. Of course, we want to have some data. We define some of them, so we don't want to always re-establish the connection, and we look at the status of them. So the scan is here, so we want to scan some. Set the scan, the microscope, the data server, the corrector. Simple check is open the column valve. Column valve is open. Let's close it just to see whether it works. Right. Doesn't let me. Closed. So we open the column valve after we check the vacuum so that it is safe. Something I haven't said before. So we open it. We have to start our data server. And you say, so the data server is something that is also stopped. Okay, that is a bit problematic. Okay, first wrinkle. I think we have to start our data server here. No, would help to open it up. I'm not quite sure what's going on, so I stopped my server. This is something I wanted to talk later, actually, when we do the parts. Let's see what it's doing, which I need to know. Okay. Where's my... Shouldn't have put it here. And see what it's doing. I have to go to the microscope to move it around a little bit, this window, but in principle, we're waiting here for the devices to come on. The idea is to have a unified interface for your microscope. You don't care whether it's a GOL or a Thermo Fisher or neon. So you always want to have the same interface, and you want to have the same surface. So now we are starting the main server. As I said, we are going through that. The corrector is from CEOS. The microscope has different parts, and they can, of course, also be from different vendors. So they should all be combined, and we do that through this PyTango server, which is actually a database. So it just routes everything through. Okay, now everything is running. And if I go back to my server, this one should still be okay. And now it's running. And it has a little bit too many pictures here. So the way it's working is we save all the different images and data on the disk and just send a link across. So through the tile server, which is part of the Blue Sky project that is developed for synchrotrons. So we adopted that and adapted that for our microscope part. Okay, so we have this problem here again. And so oh, here's my image. We can focus with the sample height, so that's what we normally would do, but we already are focused here. We lost a lot of time, so I'm not going into that. The sample has to be at the exact height of the objective lens to be in focus, so you can do that with the defocus value, which you should not change much, or the height. And then we do an aberration correction. In order to do an aberration correction, we want to be at a magnification or a field of view that works in both directions, in the reciprocal space and in real space. So the real space is our image, the Fourier transform is our reciprocal space, and we want to have the resolution of an atomic probe in reciprocal space. And what we do here is we just let that run. If I go back, if I'm fast enough, to my team viewer. So you see it's doing something. Where is my... Okay. That is terrible. Something is wrong. It's super when it's not working and worked all the time, right? Where is my tableau? The tableau is where we are. I was just on the wrong button here. So what it does is it's doing the same thing as we saw with the Zemlin tableau for very, very small angles. And we make it a bit bigger. So that you can, no, okay. Can I zoom in? No, good. So it's a magnification I chose, which is about 200,000. We go in under and over focus and in focus. And what we check is how is the image smeared out. And that is our probe, defocused. And we are looking after the under and over focused probe. In our case, we are close to focus. We can say that because our defocus, so the images are relatively similar, right? So the size of the probe is the same in the under and over focused one. And if we are, we can try that. Let's go first to the aberration corrector. So we have a 13 nanometer defocus on, and we have an astigmatism of 6 nanometer. And we have a directionality to that. B2 and A2 are also are in the order of 100 nanometer. All of these values are about the factor 2 too large for a good image. Okay, so we would have to correct that. But let's first look what it looks like when we defocus it. So I make to switch the monitors over. Okay, so we had our panel. Again, obviously. So we want to see what we're doing a bit faster, maybe. No, a bit faster. Our hand panel disappeared. And so we defocus it a little bit. So it's still a decent image. And you wouldn't by eye see what's going on. Let's see what our system says if we try that. That was too early. you cannot do two scans simultaneously, right? So we go operations, and we record that. So we first and we can check what's going on. So you see the left one, the underfocused one, is smaller than the overfocused one. So we have a small defocus value, and the focus value is a little bit large. So what we want to do is we want to correct for that. And we have values in here for the said we should be better than so threshold values for this, and we have C1 and A1 are too high. Okay, and B2 and A2 are also too high, so we want to have these two better than 50 and these ones better than 5 nanometer. And this one, what we want, that is how accurate are we going into the objective lens. We want to have that better than 0.3 milliradians. So now we corrected that. The correction is done by machine learning, by the company CEOs that refined the aberration so that they change their parameters, and it is as clean as possible for these aberrations. So we see C1 and A1 are now below 5 nanometer. E2 is good. A2 and the objective lens. I don't know what WD stands for. Nobody can tell me. So you do that till the first and second orders are corrected. So you just let it run and be done with it. Once you have the first and second orders, then you know that your probe is as round as possible, and everything else is only higher orders. And that's what we will connect next. So we run till we don't correct anything anymore. We don't know where we are. We could check that on the microscope. Oh no, here we are. So A1 is a little bit, if you change one aberration, then the other aberrations are sometimes get changed parasitically. That is not avoidable. Our system is actually we're quite happy with it. So we have very few of those. Very rarely that it happens. And we are done. Okay. Now we can check the higher orders. As you saw, I could have gotten away with only 1 point, but we okay, sorry. So let's go back. So what we do now is, instead of going only 1 milliradian out and basically are in the center at all points in time, we now go with a very high angle and with different angles. And so we want to see the Zemlin tableau. Our starting point should be as good as possible So that is 0, right? So that was where we had a round one before. And then we go left, right, back and forward. You can see everything is relatively round, independent of the angles. So our aberrations cannot be especially bad. I messed a little bit up before, but effectively we have very little aberrations. Normally when we start the day, we have a few more. You have quite a few more if you change the acceleration voltage and you load completely new values for that. Let's see what's gonna happening here. I have my rule of thumb. The first order should be better than 5 nanometer, second order better than 50, third order is better than 500, fourth order better than 5,000. We see the only one that is a problem here is D4. And if I correct now the third orders, which I can't do because I haven't defined this function. This function I actually borrowed from how we do it. There is a GUI here, and we just let it run. Obviously, what I just did was relatively boring on a daily basis, but for an educational point of view, it's of course not. So now that I have this function, okay, on the third order, there is nothing to be done. That's a bit unfortunate. I wanted to go back to a worse aligned microscope. And so we have a few fourth orders. And if we go here, and that looks on your screen, on a normal screen better than it does here. You just let that run. And the idea is that we first correct, where is it? Okay. The idea is you correct the first and second orders, as we did, till they are as small as the aberration corrector allows. And once that is done, we correct for the third orders. If you correct the third orders, you will most likely have first and second order aberrations parasitically. So you go back and correct for that. And then if you have no third orders and the first and second orders are also good, then you can correct the fourth orders. We are a little bit more adventurous when we are on the microscope ourselves, but since that is usually running when I'm driving here, I don't care. So a direct change. But what does this really tell you? We can independently mess around with our aberration corrector, right? And we are doing that so we can directly access all the different components of the aberrations and adjust them. And we don't have to go necessarily through that notebook here or through this. Okay. I change this one. Cannot make it smaller, can I? So the fourth orders we see, so we started at 0, right? So the fourth orders are above our requirements, and it changes that. After that, we changed the fourth order. Then we got some parasitic aberrations in the first and second orders, and then it changes that backwards and forward. Austin, can I ask you to get the aberration corrector out of my office? I forgot it. It's on the shelf. Okay. So this is running, and after that, it's just finished. So it does not really change anything how okay. So how can you connect to our microscope? If you become a user at our microscope facility, you get a net account on our university, and with the net account of the university and the password, you can directly use the microscope. You do not have to be here to do that. Also, with the net ID, you can do the whole thing from the supercomputer center. So normally we are not doing it on our laptop, or we're not necessarily doing it on our laptop. We have a workstation and the supercomputer center. And with the supercomputer center, you have, of course, enough power to do some kind of machine learning algorithms. In the moment, we are just trying to get to the basics here. Okay. Now we don't see quite, but apparently it stopped. Oh, no. Okay. Third orders. There's another round here. Obviously, the aberrations are have some parasitic ones on C3. So the first and the third orders, that's not quite below the requirements. So you see, we have always this parasitic one. So going backwards and forwards is a good point. I only have 5 here. If it's really bad, so and you have time, you can of course drive. Okay. So while we're waiting for that, yeah, okay. This is the third aberration corrector. Okay, you see how heavy it is. I already have a problem. That we got in Oak Ridge, so it's the first aberration corrector for a 300 kV microscope. When it was dismantled, I got that one. That was installed in about 2002. This is one of the first generations. It has about 128 power supplies. And I'm not sure how they do it now, but at the time, that were all military-grade components. So they were very, very stable, because that's what it needs. So be careful. If that drops on your foot, we have to go to the hospital, which is across the street, so it's not really a disaster. Yeah. I just don't want them to drop it. Just leave it over the chair. So it's kind of fun. How does these things work? Aberration correctors have also called multipoles. So a dipole is a north and a south pole. That is how we usually do our deflection, right? Electron goes through and gets deflected. If you do 4 of them, you have a quadrupole. So north, south, north, south, north, south. If you think of that in plus, minus, so the minus, minus one will repel the electrons, so they get squished and elongated. So astigmatism can be very well aligned with that. With a hexapole or an octapole, this is an octapole corrector. Zeus has hexapole corrector. The 6 or 8 poles, that shows that you have positive spherical aberration with those. And with those, you can correct actually the aberrations, but you have to have a lot of independent power supplies. Okay, seems like it's still not finished. It is, however, relatively close. Let's have some questions, maybe. Wechseldrehung? No kidding. Okay, so it is a rotational part of the, I'm not sure whether you see that in the chat. Alma, thank you. You are the first one who really knows that Wechseldrehung. So it is by changing the lenses, how it is rotating. So change rotation or lens rotation, that is what that is apparently. And of course, it should be rotating around the center. Super. Okay. I learned something in this summer school, so we can all go home now, right? Okay. Yeah, rotation center. Good. So do we have any other questions? No. Okie dokie. So apparently that is clean. Let's see what the microscope's doing. We can get out of here. Oh, it stopped. We can see all the values on the left-hand side are correct. If we accept this, the very nice tool provided by Zeus will tell you how much of a lens, of an aperture you can use to have a coherent illumination. Again, that's in the next one. We will go into that. But it tells you most importantly what kind of resolution you should expect. So in our case, about 70 nanometer, 70 picometer. And there's really not much to adjust here. Everything is down to the specifications. Good. So that means we can acquire images. Yeah. Where are my images? This isn't the way here. How did I do that? Okay. Get an image that is with 170 nanometer field of view. This is from this morning. Okay. This is super irregular here. I think my tile server died again. That hasn't happened yet. We can check. We have no tile server. I think the database might have crashed on all the different files that we have there. So in the break, I will go there and kill that, because we really have a lot of images on that. And so apparently that's not what it can do. But we can check still how good that was. So we go over here. We want to start this. We do the same thing what we would do on our notebook. We change the focus. I want to get out of that hole. Yeah, okay, I'm in a new hole. Okay. I think zoom a little bit more out. Let's go. See what this grain does. We zoom in. Okay. We see already some amount of atoms. And what we do now is we want to focus. And how do you do that on a nice microscope? We go to the OptiStem and say, please correct my C1 and A1. It does the same thing as before, so it changes to under and over focus and tries to figure out. So we had a little bit of an astigmatism, focus, and everything else was right. So this is for a specific sample height now, right? So we were doing it first with a relatively large view. And so small changes in height will change things around a little bit. So apparently we didn't have to do anything much. And so if we go back to our no, that's not good under any circumstances. Whatever it did, it was making it worse. Okay. Excellent demonstration. So it's back here. You are sometimes better than that. Let's go and try it at a little bit higher magnification. Maybe it's better at that one. That's not what I want to do. So we stop that here and go back to the. This is purely working on contrast. So we will see in the after lunch that is really not the way to go. So you also want to know your resolution. But when you're on the microscope, this is something you can handle. Shouldn't have changed much, right? So let's go back. No. And see what it does. Okay. Maybe a little bit better. Let's scan slower. And we look the aberrations. So we have clearly sub-angstrom resolution. We don't have a really good small, no, maybe over here, very faint, a smaller interatomic distance. So we would have to find one that we really can push for the resolutions that we got now. So we said we have corrected our microscope. As I said, we normally don't watch that anymore, so you can do that remotely, but we are really trying to do that smarter and possibly have an agent waiting or checking whether there is anything deteriorating while you're taking your images, and corrects it possibly directly on the fly. Okay, so, okay, something's coming up, possibly, who knows. Anyway, so that's it for that. We, after the coffee break, so we have 10 minutes. How long? So we have 10 minutes coffee break. Coffee is here. After the 10 minutes coffee break, we will look at the ronchograms, and the ronchogram is what we saw. Whatever I did was not very smart. Is the relation between what we see here and our probe size and probe shape exactly. Okay, close the valve. And we set, oh, in the chat, that works. Let's see what's up. 2 new messages. I can see significant scan distortion. Okay, so I was doing it relatively slowly, and actually the scan distortions are mostly the sample itself moving around and about as well. So what helps usually is if you, well, since we are on it, right? So I'm here with 4 nanometer resolution scan. What you want to do is make a whole, how many are there? 10 frames, okay, whatever. So you take 10 frames. So we still move around and about a little bit. I was messing up the thing quite dramatically. And so if we go to this one here and we look at the summed image, you actually do not have a lot of distortions anymore. And you get a relative clean image of that grain boundary here. So the scan distortions are mostly thermal part here, and actually I think how we heat up the sample. If we stop the beam, I have a little bit too much current on it, I think. So if we stop the beam, and then we scan again, you see that we are drilling holes here. On our alignment sample, close to the center, you will see a lot of particles that have little holes in them. So, so let's do a slower scan again. This is what it normally looks like. Maybe somebody went in and out of the room. I'm not there, right? So I should have closed the door. Next door, they are actually painting stuff, so I don't know. Anyway, hope that explains it. Okay, good.